The TCP/IP suite or Internet suite is a set of protocols that allows us to communicate and exchange data on the network. The suite defines how data is packetized, addressed, transmitted, and routed. The key protocols are TCP, UDP, IP, and ICMP. We see the TCP/IP suite residing here at the network and transport layer. At the network layer, the main players are IP and ICMP. IP, or the Internet Protocol, is the network layer protocol used for routing the data from the source to the destination. IP is responsible for addressing and does not have any error reporting functions. For that, we use ICMP. This is used in addition to the Internet Protocol to carry error, routing, and control messages. However, it does not exchange any data between systems. The transport layer provides data transport by using either TCP, which is a connection-oriented protocol, or UDP, which is connectionless. You will hear that other protocols ride on top of the TCP/IP suite, and those would be protocols such as those in the application layer, HTTP, FTP, or SMTP. And we need to set in our bindings the ability to use TCP/IP as pictured here in this graphic. The TCP/IP suite or Internet suite is a set of protocols that allows us to communicate and exchange data on the network. Transmission Control Protocol resides at Layer 4 or the transport layer of the OSI model. Transmission Control Protocol provides connection-oriented transport. TCP begins with a three-way handshake and data is sequenced and acknowledged. TCP supports windowing and flow control so as not to overwhelm the host. Here is the TCP header, and now we'll go into Wireshark and take a look at those field values. If you'd like to follow along, we'll go to CloudShark. I downloaded http.cap, and you can go to Export and Download File and bring it up in Wireshark. Now, once in Wireshark, what I did was, I'll show you here, it starts out with the three panels. I go to View and take off Packet Bytes. I want a little more landscape. Now, we'll bring this up and go to Frame 4. Let's just take a look at our encapsulation. Frame 4 is simply metadata about that frame. Here's the frame header, Ethernet 2, the network layer header, IP, the transport layer header, TCP, and then the data, HTTP. We're going to open up TCP. Now we can take a look. I'll float this on top so you can refer to the TCP header. All right, first we see the source and destination port. The source port is 57678. Now, sent from the client, that's simply saying, when you come back, send the data to 57678. The destination port is 80, which is associated with HTTP. Here we see stream index 0. There are no field values stream index. That's a value calculated by Wireshark. This helps you to keep track of the many different streams in Wireshark. And if we were to look at conversations, we could go to stream index 0 or stream 14 or whatever you'd like. Here we see TCP segment length 134. Now, where did that value come from? Well, I'll scroll down here and I'll place my cursor on the HTTP header. And here you see 134 bytes. Again, that's just a number calculated in Wireshark. Now here we see the sequence number 1, and it's a relative sequence number. What that means, it's in relationship to this stream, sequence number 1. It's not the actual value. If it were, it's a large number. Let's take a look. I'll right-click, and I'll go to Protocol Preferences. Now here we can uncheck relative sequence numbers. And as you see, it's a large number. It's really hard to calculate values with that large number, so we'll go back to relative sequence number by going to Protocol Preferences And then we'll put relative sequence numbers back. For example, here it says next sequence number 135. Well, that's 134 plus 1, and that's what's calculated as what's coming next. Here you see the acknowledgement number 1, and again, it's a relative acknowledgement number. And now here is the header length, 32 bytes. Normally a TCP header will be about 20 bytes. Now when we add options, that adds to the length. So let's take a look. I'll place my cursor up here at the TCP header, and then down below we see that the TCP header is 32 bytes. Now we'll scroll up here and let's take a look at the flag section. Now there's a lot going on with the flags. When you're ready to go a little more advanced, you can find out about all the flags, and why we keep track of those is certainly your devices are monitoring what's happening during the conversation. The flags tell the story about what's going on at that point in time. Now, some common ones that you'll see, of course, is the SYN flag, and that's going to synchronize the sequence numbers. We see acknowledgement, and that's, of course, acknowledging the data, push. And the FIN flag is when the conversation is over, we exchange FIN packets. And reset is when it's set, it means I don't want to talk to you, and the conversation is reset or closed. So a lot goes on with flags, and it would be good to get familiar with those as you advance because it tells a lot about the story, and it is used for a number of different reasons. All right, now we'll go to window size. Now window size, it says 46, but then there's a value here in brackets that says calculated window size, it's a larger number. Well, that's because the actual value is pretty small, and in the 80s, the window size of 46 would maybe be normal. But as you see, there's a scaling factor of 128, which gives us the true value of 5888. That's so the server knows about how much data I can send to the host without overwhelming the host. It will update if the value goes up or down. For example, if the host buffer were to get too full, the number would shrink. And as it processes the data, the number would then expand. Now we'll look at the checksum. It says unverified. Well, in a lot of cases, you'll find that we're not going to try to validate that checksum, and here's why. Now take a look down below. There's a blue dot, cyan dot, and that's the expert system. Now what is it saying is that's just chats. Okay, so if this were to be calculated, this might be incorrect, and I'll show you why. We'll go to Protocol Preferences, and here it says Validate TCP checksum if possible. Now I'll select that. And now you see it says it's incorrect, and it should be this number. And as you see, there's a little note that says TCP checksum offload. What happens is it offloads to the NIC card, and it comes up incorrect. Down below, you see the red dot and the expert system, and that's saying that there's possibly something wrong with this stream, but there isn't. So we'll go back and check that and replace that with validate the TCP checksum if possible, and that'll correct that. But a checksum is important to use because it's going from source to destination. Many things could happen. The checksum in the TCP header monitors for error detection, not correction. Now we see the urgent pointer, and then down below, then what follows, as you see over here, is options and data. Well, now here you see the options, and in this case, that options is 12 bytes. Now we know that it needs to be a multiple of 4, so let's drop this down and see what's inside. Well, you see there's the timestamp option, and that's 10 bytes, but it has to be 12, so you see no ops, which are kind of placeholders, so that it comes up to 12 bytes. And then following that, then you see HTTP, which is the data. So that's the TCP header in Wireshark, and we've gone over all of the field values, and hopefully you've got a little better understanding of TCP. Transmission Control Protocol is a connection-oriented protocol. It begins with a three-way handshake and ends by terminating the session. A three-way handshake begins by the client sending a SYN packet to the server. That SYN packet synchronizes the sequence numbers. If the server accepts, it responds by a synchronization acknowledgement. The client then sends a final acknowledgement, and then we have a connection. A socket is created, and we can begin to exchange data. Periodically, services will be refused, and then you'll see a reset. No response may indicate a firewall. You may receive an ICMP destination unreachable packet, and a code might indicate the network was unreachable or the host was unreachable, but most likely the target port was firewalled. The host might try again with another SYN packet. The connection can be terminated in one of several ways. The connection can time out and will be closed. Or no password was sent, so the connection was reset. Or we'll see an exchange of FIN packets, and this indicates a normal termination. For a normal termination, we simply see an exchange of FIN and FIN-ACK packets from the client to the server and the server back to the client, and this will close the connection. So let's step through the handshake and termination. I'm here on CloudShark, and you can either follow along in CloudShark, or you can go to Export and download the file and open it in Wireshark. I've opened this capture in Wireshark, and it's almost a perfect example of a complete conversation. I'll scroll up so you can see that it's really a small capture. But let's take a look at the flow graph. We'll go to Statistics, and we'll go to the flow graph. And there's no need to filter it because its entire conversation is simply with the client to the server. Now let's take a look at the top 3 packets. There's where you see your 3-way handshake. And then down below, we see an exchange of data. And then somewhere in the middle, you see quit and closing connection. So we now know it's time to terminate the session. And the last 4 packets are where we close the conversation. I'll close that, and now let's take a look at the 3-way handshake. I'll scroll up here and give us a little more room where we can take a look at frame 1. Let's just first start with frame 1. Now, when we look at frame 1, we have a frame header, we have the IP header, and the TCP header. As you notice, there's no data. There won't be any because it's just a handshake. No data is exchanged. You can also see then up here in the upper right-hand corner, length equals 0. So let's take a look at the TCP header. This indicates what's going on if we take a look at the flags. And I'll drop this down. And here you see the SYN flag set. Again, that's from the client to the server, trying to initiate a conversation. Now, with that first packet going from the client to the server, comes with it some options. If I place my cursor on the TCP header and then look down below, the TCP header is 40 bytes. The TCP header is 20 bytes at least, but with options, it's more now at this point, it's 40 bytes. But let's take a look at the options. Here's your options, and we'll drop this down, and you can see what it is the client communicating to the server what options would I like to agree upon. And so you understand, for example, the following. Client is saying that the maximum segment size is 1460 bytes. Also, SAC is permitted, and SAC is selective acknowledgement, meaning keep sending the data even if it's not in order. I'll put it in the correct order. Here we see timestamps and Windows scaling. Now keep in mind, it has to be a multiple of 4. Now with each of these, and if you look down below, you can see the size of each of those options. Windows scaling is 3 bytes, so we have to add a no op, which is essentially a placeholder to bring that total up to 20 bytes. And then that with the TCP header gives us our 40 bytes. The server then responds with a SYN-ACK, and I'll scroll down here, and here you can see the acknowledgement flag and the SYN flag. Now keep in mind, that SYN flag is set only on the first 2 packets of the 3-way handshake. After that, you won't see it again in that conversation. Now we'll bring this up, and take a look at the TCP header, and again, it's 40 bytes because the server is sending the server options. And as you can see, those are the following options the server sends to the client. Then we go to frame 3, and that's our final step in this, and let's take a look at the flags. Now we see that the acknowledgement flag is set, and that means the conversation is ready to begin. After this, we can start to exchange data. And at this point, you can see the TCP header is dropped to 32 bytes because there are a few less options, as you can see down below. Now we'll bring this back up, and now we'll take a look at the end of the conversation. Down below, we'll go to frame 12, and here's where you see the exchange of data from the client to the server. Now here it's saying an acknowledgement, and that acknowledgement is probably at the end of the conversation where the client is saying that it's acknowledging that it's received whatever data it's received from the server. The server responds with a fin ACK saying, "I'm pretty much done with everything. We can close this connection." Then the client then responds again with a fin ACK, and then we see our final acknowledgement, and that will then close the connection and terminate the session. So as you can see, TCP is a connection-oriented protocol where you will see a three-way handshake and a teardown of the session. User Datagram Protocol is a connectionless protocol for data transfer. We see here in the OSI model, UDP is in the transport layer. UDP is a lightweight protocol. It provides connectionless transport layer service, and there's no handshake or connection process. UDP doesn't have any ordering or reliability services, and there's no teardown. UDP is a lightweight protocol that's great for time-sensitive applications, such as DNS, voice over IP, routing information protocol, or trivial file transfer protocol. Here we see the UDP header. It's always 8 bytes long, and it includes the source port, destination port, length, and checksum. Now that checksum is used for error detection, not correction. The UDP checksum is optional with IP version 4, however, it is mandatory with IP version 6, primarily because IP version 6 doesn't have a checksum. Now let's take a look at a UDP header. I'm at CloudShark, and if you'd like to follow along, you can download this file. I've opened it up in Wireshark, and what I'll do up here is go to the display filter, and I'll type UDP. So there are my DNS packets, and what we'll do is just take a look at the user datagram protocol. I'll double-click and pop out this frame. And again, this lightweight protocol only has 4 fields: the source port, the destination port, the length, and the checksum. Now that's pretty much it for UDP. So while I'm in here, let's take a look at some other things in Wireshark. Let's go to statistics. If we go to statistics, you can see there are a lot of choices, and for more advanced training, we will get into those. But for something really simple, let's just take a look at capture file properties. Now, when you open this tells us a summary about this file. Now you can see the capture and what it knows about the hardware or the operating system. Again, what it knows, it will put in there. Here you can see when this packet was captured, 2011, and some more information about the statistics. Now down below here, in the next generation, we are able to put comments in the file. Now this would be handy if we were to share this information with coworkers. So for example, I might want to say, take a look at frame 29. And I'll just say save comments, and then we'll close it. Now if you take a look up here, there is an asterisk that is right by the title. That is because it knows that there's a comment and you will want to save that so someone can reference it when they open it up. Well, we'll go back into statistics again. Now I'll drop this down. And another handy tool is a protocol hierarchy. Now this is helpful if you are taking a look at protocols that are traveling on your network, and you might want to see if there's anything that shouldn't be on your network. So this is a simple capture, nothing's really standing out, but again, it's a nice handy tool. I'll close that. Another thing is we talked about coloring rules. Now they're there, and in some cases I do take them off because they're distracting. If you go up here under telephony and just hit that one time, it takes the coloring rules off. And that is something that's reflective of the older versions of Wireshark and Ethereal. And sometimes I take it off because it's somewhat distracting, but I'll put it back on. Now there's another thing in statistics that's interesting, and we've talked about some of the things with conversations and endpoints. We'll take a look at endpoints. Now remember, the endpoints are the two sides of the conversation. These are the endpoints. If we go into the conversation, here you can see details about the conversations. And in this case, we have minimal information. It's a very short capture. But if we go into the one conversation and we have a little bit more detail here, I can right click and I can say apply as a filter and selected. And here you have choices whether you want A to B, B to A, or both ways. And I'll say close. And that puts that conversation filter right up there, and it runs it for you so that you can see the whole stream. So really, that's all there is about UDP. And again, I wanted to share with you some other things found in Wireshark. So UDP is a connectionless protocol for data transfer. The Internet Protocol resides at the network layer of the OSI model. For this segment, we'll focus on IP version 4. The Internet Protocol is responsible for addressing and routing. It's connectionless, meaning it's best effort. For example, if you were to send a letter general delivery, it will get there, but there's no guarantee. But we can provide quality of service to push the data along a little faster. Here's your IP version 4 header, and as you can see, we have several fields, and at the bottom, options and data. Let's take a look at an IP header. I'm in Wireshark and I've expanded one of the frames, and we'll take a look at that header. And on the right-hand side, you could follow along. All right, the first field is simply version, and in this case, it is version 4. Not much there to show. This tells us the header length, and it is 20 bytes, and I can confirm if we go and place my cursor up on the top and then look down below that it is 20 bytes. This field value here is called differentiated services. That relates to what's called the type of service. Now keep in mind, 0 is best effort. It's not prioritized. But in certain cases, we want the data to be prioritized and moved along a little faster. The total length is the header and any data that follows. And here we see 1340. Now the next 3 fields relate to fragmentation. Those are identification, flags, and fragment offset. The specification stated that IP was responsible for addressing and fragmentation. Now that was a long time ago, but things have changed. We don't see fragmentation so much anymore. So those 3 fields you see, the first one is identification. So in the case of a fragmented packet, you see a number of different fragments. You'll need to identify them to put them all back together. Then there's the flags, and I'll drop this down. Now you see the first one is the reserve bit, and that's not ever used. And the second one is don't fragment, and sometimes that's 0, but a lot of times it simply says, don't fragment me, don't break me apart. Now if we were to fragment, in some cases you will, for example, if you're in a virtual environment and you use jumbo frames, well then you go back out to the regular network and it's a lot smaller and you have to fragment. So in this case you'd see more fragments and that bit would be set. And the last field value in that row is a fragment offset. And that identifier would help you to put back the fragments in the correct order in the correct place. The next field is the time to live value, And that's essentially how many hops it takes around before it goes to 0. And if it does go to 0, then it's no longer going to exist. The time to live value was in order to prevent the packets from going around and never getting to their final destination. Now, this you see the protocol TCP. That protocol field is what follows the IP header. And down below here you see TCP, so that's what it identifies. And then you see the header checksum, and in this case you see the validation is disabled. And we do disable the validation because sometimes it's offloaded and the checksum's incorrect. So it tells you what it is, but it is not checked. And then down below here, this is where you see your source and destination IP address. Then after that, you see any data that will follow. So that's the Internet Protocol version 4. When we take a look at IP version 6, you'll see significant differences. And although the headers are significantly different, they both do the same thing. They provide addressing and routing on the network. Internet Protocol version 6 has a larger address space, a streamlined header, and eliminates the need for IGMP and ARP. In this segment, we'll review the field values of the IP version 6 header in Wireshark. IP version 6, like IP version 4, resides at the network layer of the OSI model. First, let's talk about the features of IP version 6. We'll start with the expanded address space. IP version 4 has a 32-bit address space and is represented by a dotted decimal notation. IP version 6 uses 128 bits in the address space, and it's represented using hexadecimal notation. In addition to the expanded address space, IP version 6 supports both stateful and stateless auto-configuration. With IP version 6, there's no broadcast. Instead, it uses multicast to communicate with multiple hosts. In addition, there are optional extension headers that you can use with IP version 6, including fragmentation or IP security. IP version 6 is still a connectionless best effort protocol that requires the use of ICMP version 6. The main enhancement, as you see in this illustration, is that in contrast to IP version 4, IGMP and ARP are not necessary with IP version 6. Now let's talk about the streamlined IP version 6 header and compare IP version 6 with IP version 4. You'll see that there are a lot fewer fields in IP version 6. First, the Internet header length doesn't exist in an IP version 6 header. The next 3 fields in an IP version 4 header include identification, flags, and fragment offset. And those had to do with fragmentation. In contrast, IP version 6 seeks not to fragment, so there are no fields that deal with fragmentation. You can fragment, but you'll need to use an extension header. The time to live value still exists in an IP version 6 header. However, it's called hop limit. And there is no header checksum in an IP version 6 header. I've opened this packet capture IP version 6.pcapng. If you'd like to follow along, I've included it in the exercise folder. Let's start with the field values of the IP version 6 header in frame 1. Now I'll just go to frame 1, which it's highlighted, and I'll just move this up so that we can see a little more of the header. Then I'll drop down the caret so we can see all the field values. The first field is the version, which is version 6. Not much to see there because we know what the version is. But the next field value is called traffic class. Now, this has to do with quality of service. The default is 0, meaning best effort. But then we see the flow label, which is used by routers to prioritize packets containing delay-sensitive data, such as voice, video, and multimedia. Now, it's not uncommon to see a zero value, as it's not always being used, but in this case, we see a value. Next, we'll look at the payload length, which is 144. Now, the payload length is any header or data that follows the IP header. So let's take a look. Now, down below, we see the ICMP version 6 header. And I'll place my cursor here. And then down below on the status bar, we see that it's 144 bytes. It says the next header is ICMP version 6, which we know, and the hop limit is 255. And the last two field values are the source and destination address. And that summarizes the IP version 6 header fields. ICMP, or Internet Control Message Protocol, resides at the network layer of the OSI model. ICMP is an integral part of the Internet Protocol and must be implemented by every IP module as it's part of the original RFC. The fact is, the Internet Protocol would be nothing without ICMP. It's a very important protocol. With ICMP, there is no data exchanged. It's simply error reporting. And it's also used by the utility ping for echo request, echo reply messages. As we see here in this graphic, we can split the ICMP messages in two categories: error reporting and queries. For error reporting, you could have things such as destination unreachable, source quench, or time exceeded. For the query, you'd see echo request reply, timestamp, or address mask. ICMP messages are transmitted within an IP datagram. So here we see an illustration of the IP header followed by the ICMP message. Within that ICMP message, you'll see some commonalities, such as the type, the code, and the checksum. The contents will really depend on the type and whatever possible code that you might see. IP is unreliable and doesn't guarantee delivery, so it's important to notify the sender when something goes wrong. ICMP is used to give feedback about network problems that are preventing packet delivery. When an ICMP error message is sent, the message is always going to have the IP header and then the first 8 bytes of the original datagram that caused the error. As we see here is an example: destination unreachable, the type, the code, checksum, and then the internet header and the first 64 bits of the original datagram. I'm at this web page IANA, and here you can see all of the different types of ICMP messages. There are quite a few, but I want you to pay attention here. As you can see, there are several that have been deprecated for one reason or another, and you should avoid using them. The one that you will use, and is important to use, is the Type 3 destination unreachable. Within that, you see the different codes, such as the network is unreachable, the host is unreachable, or the protocol is unreachable. So let's take a look at a couple of different examples. I'm at Packet Life, and I'm going to take 2 of these packet captures: ICMP fragmented, and then here this traceroute MPLS. The first one I've opened is ICMP fragmented, and in this case what we can see is this is an echo reply. So we see that it tests for reachability and is able to reach the host, and we're able to reply, yes, I did reach the host. So we see the IP header, and then within the ICMP header we see the type, the code, and the checksum, and then data, which is essentially nothing. So nothing bad happened, it's just a test for reachability. Now in this example, this is a trace route. We know with trace route, it purposely times out, so it's going to report back that I was able to get to this hop and then report how long it took. It comes up black because it thinks it's an error, but I'll take that coloring off. But what might be fun is, let's go to the statistics and do a flow graph just to show you how it made its journey, and you can see all of those as it's going from one hop to another and then reporting back. Now, because it's coming up as an error, we can see exactly what happens, as we know that if there's an error message, the message is always going to contain the IP header and then the first 8 bytes of the original datagram that caused the error to be generated. So in this case, you see there is your time to live exceeded. So there's your IP header, and then we'll blow out the ICMP header. And as you see, the type, the code, and the checksum. And then in that, you see the IP header and the first 8 bytes of the original datagram. So those are 2 examples of ICMP. ICMP is a powerful protocol, but we have to understand that it's also used in malicious ways. For example, ICMP is used in reconnaissance by Kali Linux. It can be used to do reconnaissance, to do a ping sweep, or to evade firewall rules. So the question is, what type of ICMP packets are you going to allow? The only really essential ICMP traffic is type 3, that's your destination unreachable, and then the codes that fall within that. The others are optional. The type 0, 8, and 11, those would be optional depending on whether you would like to allow those on your network or not. So Internet Control Message Protocol, or ICMP, is used by routers, intermediary devices, or hosts to communicate updates or error information. ICMP is essentially a scout for the Internet Protocol, making sure the route is clear and communicating any errors. ICMP version 6, like ICMP version 4, resides at the network layer of the OSI model. ICMP version 6 is a very important protocol. It must be implemented by every IP module. Now, we've said this before, but now let's take a look. We'll go to the source. I'm at RFC 4443, and then right here it states ICMP version 6 is an integral part of IP version 6, and the base protocol must be fully implemented by every IP version 6 node. Now, just like ICMP version 4, node data is exchanged. It's used to communicate updates or error messages, and it's also used by the ping utility echo request, echo reply. Now here we see the IP datagram where we see the IP version 6 header, followed by the ICMP version 6 message. Now that ICMP message is just like IP version 4, where you see the type, the code, the checksum, and then the contents will depend on the type and the code. But unlike ICMP version 4, ICMP version 6 has a lot bigger role. Keep in mind, IP version 6 does not have any ARP or IGMP. As a result, ICMP version 6 assumes those 2 roles. The messages include error messages, informational messages, neighbor discovery messages, including the neighbor discovery protocol, and group membership messages that includes multicast listener discovery messages. We also, of course, have error messages that include destination unreachable, packet too big, time exceeded, and parameter problems. The informational messages include echo request and echo reply. I'm at packet captures on packet life, and you can follow along if you like. We'll take 2 simple examples: ICMP version 6 echoes and IP version 6 ndp.cap. Now I've opened up the echoes, and that's just a test for reachability. And as you can see, we have our ping request, ping reply. Pretty simple. And down below, you can take a look. You have your IP header and then your ICMP version 6 header, and then the information within it. Now, sometimes you might want to just follow what is happening there with ICMP. And if you right-click and we say follow, well, we can't because there's no transport layer protocol. This isn't an SSL stream or an HTTP stream. But we can do this. Let's go to Statistics and Flow Graph. You can open the flow graph, and there you can see the test for reachability with the request and the replies. And then you see the neighbor discovery protocol, and there's a lot of activity going on within this. We see the multicast listener report, neighbor solicitation, and neighbor advertisement. Again, I'll take a look in statistics in the flow graph, and here you can see the flow as the traffic is going back and forth, communicating to other devices on the network. And if we did take a look at the neighbor advertisement, and we'll blow out here ICMP version 6, it has some options and it's telling a little bit about what's happening. Here you see the link layer address. Here we see a router advertisement, and there are some options there as well. We'll drop this down and scroll down. And with this, you see the link layer or MAC address, and MTU, that's 1500, and then prefix information. So ICMP version 6, like ICMP version 4, is a very important protocol. But unlike ICMP version 4, it assumes a couple of different roles, and that is because IP version 6 doesn't use ARP or IGMP, and that is taken care of by ICMP version 6. Let's do a challenge. First, you'll need to go to Packet Life and download and open a packet capture in Wireshark. You'll select this one, IP version 4 SMTP. Select Download and open it in Wireshark. Then go through and answer the questions. Then come back and see how I achieved the challenge. This challenge should take you about 10 minutes. Okay, let's get started. Okay, how'd you do? You'll want to have the instructions handy so that you can follow along. Now I have the packet capture open, and the first question is, click on Statistics and Protocol Hierarchy. Now we go to Statistics, and there's a lot of things that we can choose from, but what we want is Protocol Hierarchy, and we'll select that. And this tells us about the protocols that are within this packet capture, and it wants to know how many Simple Mail Transfer Protocol packets there are. And here we can see there are 5. Now we'll close the window. Now the next thing is we want to take a look at the conversations. Click on Statistics and then Conversations. But before I go there, I want to show you the next line is endpoints. Conversations is communication between two endpoints. So let's throw our focus on that. Now, once you open it, and as you can see that the tabs are set up so we can look at Ethernet, IP version 4, IP version 6, TCP, or UDP. So we want to take a look at the Ethernet conversation, and then down below it says name resolution. Check and uncheck the name resolution box. And what are the results? So we'll check it, and then we'll uncheck it. Now, when I check it, we see some writing. Now that represents the first 6 bytes of the MAC address. In the frame header, the addressing we use is the MAC address. And the first 6 bytes represents the organizationally unique identifier. And as you see, we see Hewlett-Packard and VMware. Now using this name resolution won't hurt anything because it comes from a file. Now I'll close that. Now we want to find the first TCP handshake. And what I want to do is we take a look at this, and as we see in the right-hand side, the intelligent scroll bar. But for this exercise, I want to take off the coloring rules, and we'll just select right here. All right, so now we see that frame 1, 2, and 3, or packets 1, 2, and 3, are the 3-way handshake. Now the 3-way handshake is what's going to establish that conversation. So the question is, number 4, what is the IP address of the host that started the handshake? All right, so we'll go down below, and you can see here It's up above under source, but I'll take a look at it down below. And here we see the source is 192.168.20.70. I'll pull this up and we'll place my cursor on that TCP header, and I want you to take a look down below. That shows us the size of the TCP header on frame 1. Now, the destination port will indicate what application the host wants to use on the serving host. So let's take a look here, and we'll drop down the TCP header, and here we see what is the client's port. And this is that temporary port that just throws it out there and says, when you return the data, return it to port 54557. So that's the client's port, 54557. Now the question is, what application does the host want to use on the server? Well, the destination port is 25, which is related to SMTP, which is an email server. All right, we'll pull this back up. And the next thing is number 7, go to frame 5 and expand the IP header. We'll go to frame 5, and then we'll expand the IP header. And the question is, what is the time to live value? And I'll place my cursor there. Time to live for this frame is 64. I'll pull that up. Number 8 says, in the lower left corner is the expert system. What color is the circle? And if you take a look down in the lower left-hand corner, we see it's blue. And what does that color indicate? Well, let's just open it up, and we see that it indicates chat. Now, chat provides information about typical workflow, such as TCP window update or connection finish. Nothing really bad, just information about what's happening. All right, I'll close this. Now, one other thing is, in order for the host not to be overwhelmed, we have the windowing feature. So as you can take a look down below, and I'm going to expand that TCP header. Make sure I'm on frame 5. And I want you to take a look at the window size value. It's 229. But there is scaling, as you can see, the scaling factor. So there is the calculated window size, and that means that's kind of the true value of the window size. So the server can send up to that amount of data before it overwhelms the host. Now I'll right click and we can say apply as a column. And as you can see here, and I'll pull this down so you can see now we have the calculated window size added to a column value. Now I want to take it off by going right click, and I'll just uncheck that and take off calculated window size, and we've removed that column. Okay, so that's the end of our challenge, and I hope you had fun. domain name system, or DNS, resides at the application layer of the OSI model. DNS is an important protocol as it maps a host name to an IP address. It uses UDP port 53 for requests and uses TCP port 53 for a zone transfer. With DNS, a client will send a query to a DNS server for an IP address. The server will respond with the information. The server can ask other DNS servers for the information. With DNS, there's a number of types of records. Some commonly seen records are a Type A record. That's for an IP version 4 address. You might also see a mail exchange record. This will redirect mail to a mail server. And a Quad A. This shows the IP version 6 address. Now, why is it called Quad A? Well, IP version 4 is a 32-bit address. IP version 6 has 128 bits. It's 4 times as large as an IP version 4 address, and that's why it's called a Quad A. Within the DNS header, you'll see questions, answers, authority resource records, and any additional resource records. Now, the question from the client is slightly different from the answer from the server, and we'll take a look at that in just a second. I first want to direct you to this website, and where you can find out a lot more information about DNS. Now, within this, you'll see that there are a ton of RFCs that deal with different issues on DNS. Such as here, DNS Zone Transfer Protocol, DNS Blacklists and Whitelists, and DNS Security, and a lot more. So there's a lot more to DNS, but let's just take a look at a simple example. I'm at this packet capture and there is a lot of packets, but I just want to filter by a DNS, and I'll go to the display filter and type DNS. Now down below, you'll see that there are 12 displayed. But let's take a look at just one single transaction. I'll go here to the standard query and we'll pull this up. And when we drop this down, you see the transaction ID. Now it says down below response in 80, and it knows that because it matches that transaction ID. I'll right click and we'll say apply as a filter, and it will run that. Now we have them together. Well, now let's take a look at the query first from the client. So using UDP, you see that it offers a high number port, and then it goes to the server on port 53 for a query. Now we'll drop this down, and here we see the query. And first we see the transaction ID, and then we drop this down, and these are the flags that are set. Now first we see that the first one is a 0. That means that message is a query. Now this flag means recursion desired, do query recursively. Now there are 2 types of queries, an iterative or recursive. An iterative query would be a server is unable to provide an answer, so the client has to go back out and retrieve the answer. What I would like you to do is recursive query, and that means the server will look on behalf of the client. As you can see, recursion is desired. Then down below you see I'm asking one question, and please give me the IP address for this site. Now let's take a look at the response. Again, using UDP, source port 53, and then return to a high number destination port. And then we'll take a look at DNS, the response. So again, we see the transaction ID, so we kept those together. And then you look at your flags, and there you see a response. The message is a response, and we know that. But then down below, the server answers. So as it says here, recursion desired, do query recursively. And the server responds, yeah, recursion is available. The server can do that recursive query, and that's a good thing. Now, as you can see, there is 1 question and 2 answers, and let's take a look at those. Here's the question to find that IP address to that website. And then let's go and look at the answers, and I'll pull this down, and as you can see here, the information on both of those answers, you see that there are two answers. Within that, you can see the time to live value is 1489. Now, what does that mean in a DNS header? Well, when we have a record that's returned and you have an IP address and you have your answer down below here, what is it saying is that that record that's going to be held in the cache on any server or even at the host is how many seconds it can live in the cache before it goes away. So the time to live value means after 1,489 seconds, it goes away and you'll have to re-request that information and it will most likely be sent back to you. So there you see a standard query and a standard response. And as we understand, DNS is a very important protocol that provides a host to IP address translation so that data can transact on the network. Dynamic Host Configuration Protocol works at the application layer of the OSI model. DHCP dynamically assigns IP addresses on a local area network. DHCP uses UDP for transport, and the client will use port 68, and the server will use port 67. DHCP uses what we call the DORA process: discover, offer, request, and acknowledge. Let's take a look at the DORA process in Wireshark. I captured this traffic after first going into my command line and I issued an ipconfig release, and then I went back in and issued ipconfig renew. So I got rid of my IP address and then I got a new one. So when we go up here to the display filter, we're looking for DHCP, but the actual filter is bootp. Okay, so now let's take a look at the first one. As you can see, that's DHCP release, and that means I'm giving up my IP address. And you're seeing that what we gave up was the .129, and now my client address is 0000. All right, I've gotten rid of it, but then the next step is to go through the DORA process. Now, take a look at that transaction ID. Now, we know that I don't have an IP address, so the server keeps track of who I am by that transaction ID and my MAC address. So the first step is to go through the DORA process by saying a discover packet will be sent out as a broadcast. Now, this packet is essentially saying, I need an IP address. Anybody? Does anybody have an IP address? Now, this goes out as a broadcast in hopes that a server will hear and respond. So as you can see that the message type is the boot request. Now I'll pull this up and I will tell you that there are a lot of different options with DHCP. But the one I want to show you with that discover packet is requested IP address. What I'm essentially saying in that original discover packet is I'd like the same IP address as what I had before, that .129. Now we see the offer. The DHCP offer comes from a server. Now understand, on an enterprise network, you most likely will see two offers responding. So it'll come from two different servers. Now the offer's saying, I have an IP address and you probably will like it. Why don't you try it? .129. It knows I want the same one and it says, no one's using it. Go ahead. Why don't you try it? The next step is for the client then to go back out and say, yeah, I think I do want that one and let's go to it. So I'm going to request it. And again, I want the requested IP address and I would like that IP address. Could I have it? Well, sure. So the server responds with the final step in the DORA process by sending an acknowledgement. And now I'm sending my reply, and again, the same transaction ID. And here we say your client IP address is .129. Now, if we go down, it of course gives the MAC address and then the options. But what happens is, remember, when I get a dynamically assigned IP address and it's not static, I'm only borrowing it. So down below in these options, this gives what we know as the lease time. And in this case, you see it's 7 days. And that's pretty standard. It's either 7 or 8 days. Now what happens is, after 50% of the time, or 3 days and 12 hours, I have to go and issue a renewal. And then you see after 87.5% of the time, I go into rebinding. And I then make sure that I'm able to keep that IP address. So Dynamic Host Configuration Protocol is dynamically assigning IP addresses to hosts on a local area network. DHCP uses the DORA process: discover, offer, request, and acknowledge. File Transfer Protocol resides at the application layer of the OSI model. FTP transfers files using TCP ports 20 and 21. Port 21 is the command channel on the FTP server, and port 20 is the secondary port used to transfer data. Once you get into the server, you're going to see a series of reply codes, and this will tell us the state of the data transfer. Classic FTP uses what's called an active request, meaning the client initiates that data transfer and the FTP server maintains state information, such as current directory and any user authentication. However, most likely you're going to see a passive request, and this is preferred for clients that are behind a firewall, as it's more secure, because the client, not the server, initiates the transfer. Basically, the client says to the server, "You sit back, I'll do the driving." It first asks the server to accept a data connection over a new TCP port, and the server normally accepts with a code 227, and then the server will provide a port in which to make the connection. I have this packet capture here, which is FTP example, and this is a standard FTP exchange of data. Now, first of all, I will tell you that it's in plain text, and there are very, very few open FTP servers out there. In most cases, it's using some type of secure connection or encryption, but we'll be able to see everything because it is in plain text. So the first thing you see is the initiation of the contact from the client to the server, and there you see a three-way handshake. Now I'll go into packet 5 and I'll right-click and I'll say follow the TCP stream. And we'll open this up. And this is very classic. What you see is something on there is a banner which you would read, and it would give some warnings about what the site's about and what you should or shouldn't do. It will provide an anonymous login, and it says send your complete email address as your password. Then once you get in, the anonymous access is granted. However, restrictions will apply. Now, down below here, we can see that that is asking for a passive. So the client says, could we go into passive mode? Then you see the response from the server 227 saying, yes, we'll do that. We'll enter passive mode. And then it replies with this set of numbers. We'll go into that in just a second. Then you'll see the complete exchange, and then at the end where it says the transfer is complete, and that kind of ends it. But let's go into that passive. So I'm on frame 50, and we'll open this up. I'm going to go down to the passive mode. So the request command passive. So that's saying from the client to the server, can we go into passive mode? The next packet is 51, where it accepts that passive request. And we'll go into the FTP header where it says entering passive mode. And when you see that series of numbers, you may be wondering what that is. Well, what it is the IP address and then the port number. All right, so how does that work? Well, each of those represents one of the octets in an IP version 4 address. So down below here, you can see 170.225.15.40. But what about these other two numbers? And it's coming up with a really large number. Well, it is a formula, and it has to do with those two numbers. So the formula is that first number multiplied by 256 plus the second number. So let's do that. 232 times 256 equals plus 57. And that gives us 59,449, which is, as you see, the passive port. And then the data transfer continues. And then it eventually gets what it needs, and then you would most likely close out the connection. FTP is a way to transfer files to an FTP server and update the information. Although active was the original way to use FTP, more likely you'll use a passive connection where the client will initiate the data transfer. Hypertext Transfer Protocol is an application layer protocol for browsing the web. HTTP has been in use on the web since the early 1990s. It's a client-server model that uses TCP port 80 by default, but can use other ports as well. With a typical transaction, the client will send an HTTP request and indicate what the client wants. The server then will respond with a status code and server information, and then any requested data. Now, there are several status codes within HTTP, but most of the time we're going to get a 200 or success, meaning everything's okay, and the data will follow. Most application layer protocols have a typical format where you have the frame header, the network layer header, and the transport layer header, followed by the data. Now, the frame header, the network layer, and the transport layer header remain pretty much the same. The data in the application layer header changes according to what's happening in the conversation and whether it's from the client or from the server. So with HTTP, you could possibly get the HTTP header information that includes the general header, request and response header, or the entity header. And then within that, you'd have the HTTP body, which holds the HTML code or the web page so that it can rebuild that in your browser. I've opened up this packet capture and we can take a look at some HTTP traffic. There's a lot of packets here, and one thing we can do is take a look at the conversations by going to Statistics and then Conversations. Now, once you open this, there's a lot of column headers. And what you could do, and in this case, we're going to sort by bytes so that we get the top talker. Now, as you can see now, that highlighted area, we can do something with that. For example, I can apply a filter. I can do this. I can either select the entire conversation from A to B, that would be from the client to the server, from just the client to the server, or from just the server to the client. I'll select all of that, and then that will run that filter, and then we'll close that. Before beginning anything, we start with a three-way handshake. Now, as you can see, there's no data exchanged, it's just a handshake. And then once that handshake or connection is complete, then it goes into our first HTTP request from the client. We'll pull this up, and as you can see, the client is saying, I would like that picture of the blue goat. The host is goatrodeocheese.com, and then a little bit of information about that client. For example, what's the operating system and what their browser is. And also other information, including language, and in this case, we want it to be in English. Then down below, we now see the response from the server, and it's saying it's a 200 status code, which means it's okay. Everything is good, and now I can start to give you what you need. It's using HTTP version 1.1, which is the most commonly used version, and the server is OpenResty, which is the third largest web server in use today, behind Apache and NGINX. It says, well, what the content is, and it's an image or JPEG. And other information about the server. Now, what I can do is right-click, and I can say follow the TCP stream. Now, in this case, this shows all of the connections that are happening within that single stream. And there's more than one. And in fact, when you're retrieving data and objects off of a web page, you'll have more than one stream most of the time because you want to be able to retrieve those objects quickly and rebuild the web page in your browser quickly. Now, as you can see, the red is from the client and the blue is from the server. And I'm going to scroll down and you'll see that there's a number of requests and responses. Here's another one, GET, and then the HTTP status report and the HTTP status code, and then the response. And there are a few of those within this single stream. All right, now I'll close that. And then just one more thing we'll take a look at. When you're getting this data from the web server, which is very common, you see a number of areas that are black. And if this is going to happen consistently, you might want to look into it. One thing we can do is go to statistics and then run a stream graph. I'll use the TCP stream graph time sequence or Stevens graph, and we'll open this up. Now, as we see, that's the server to the client, and we can switch directions just so you can see, but we want it to be from the server to the client. All right, so when we follow this, this is showing this line's going up. It's all good. We're getting the data, and then we're not. So this is showing nothing's happening here. As you see, that's a 10-second delay. And I'll move this down, and as you can see, it's a keep alive. Nothing's happening. It's just still waiting. And we go here, and there's a 7-second delay. Then we have the data is coming in. It's good. Well, a little hiccup here, and up, and now we have a 9-second delay. Then a 10-second delay, 10-second delay, and more 10-second delays. Where really nothing's happening. So I'll close this and you can take a look at this and see that it's pretty much stalled. But at some point at the end of the conversation here, you see that the client and the server both agree they both have what they need. And then you see the exchange of the FIN and the ACK packets from the client to the server and the server to the client. And that effectively closes the conversation. So HTTP is an application layer protocol for browsing the web that's been in use since the early 1990s. It uses a client-server model using TCP port 80, but can use other ports as well. On a local area network, the data link layer uses the MAC address of the destination machine rather than the IP address. Address Resolution Protocol resolves an IP address to a MAC address on a local area network. Let's take a look at where ARP resides in the OSI model. It resides in between Layer 3 and Layer 2. And that's because when we take a look at it, it doesn't have a network layer header, it doesn't have a transport layer header, it's simply doing a resolution. In addition to the ARP request ARP replies, you might also see a gratuitous ARP, which is a test for duplicate IP addresses on a local area network. If you'd like to follow along, go to packetlife.net, and I selected ARP, and this last one here, ICMP across.1q.cap. I've opened it up in Wireshark, and there really aren't a lot of packets in this capture, but we'll just take a look at ARP. We'll put a display filter in, and you see there are a couple of types. One is the gratuitous ARP, and as we talked about, that is simply a test for duplicate IP addresses on a local area network. But then down below here, we see the ARP request and ARP reply. Now let's take a look at the request, and we'll drop this down, and the hardware type is the type of data link type in use. And here we can see it's Ethernet. And we see the protocol type IP and the hardware size, which is 6 bytes, and that is the length of the hardware address. And the protocol size is the length of the protocol address. Here we see the opcode, and it is a request. Now it's from the sender here, which you can see this is the sender's MAC address, and this is the sender's IP address. The target MAC address is a broadcast. And remember, it doesn't know the MAC address, so it goes out to everyone on the network. Everyone on the network hears it, but only one should respond. And then down below here, you see this is the IP address. So looking up here in packet 3, it says, who has this IP address? Could you tell me who has this IP address? Then we see a reply. And it has the same fields, except it does provide the answer. Now we see the opcode is a reply, and the sender MAC address is where it's coming from, and there's the IP address, and then it's responding to the one that sent the ARP request. So address resolution protocol sits in between the network layer and the data link layer to resolve an IP address to a MAC address on a local area network. Let's do a challenge. First, you'll need to obtain the Wireshark Essential Training Challenges and Links document, and scroll down where you will see detailed instructions, which will look like this. Now, in this challenge, you'll need to obtain 2 packet captures, and I provided you with the links. Now, complete the challenge, and then once you're done, check back to see the solution. This challenge should take you about 10 minutes. Good luck and have fun. Okay, let's go through this challenge together. You might want to have the document handy so that you can follow along. First, you are to go to cloudshark.org and examine this packet capture. Now, once in, you are to go to Analysis Tools and select GeoIP World Map. And the question is, what are the endpoints? Well, the endpoints are either side of the conversation. So let's take a look. We'll go to Analysis Tools and GeoIP World Map, and we'll let it run. Now, the GeoIP World Map is a handy little feature that's built right into CloudShark. Now, here we can see the endpoints. One is in France, and one is in America. And we'll close that. Next, you are to open the file in Wireshark. Well, you'll need to download it. So go to Export, Download File, and I always select Download the original file. Now you've opened it in Wireshark. So let's go to the next step. In DNS, a time-to-live value specifies how long a resolver is supposed to cache the DNS query before the query expires. So the question is, in frame 2, what is the IP address of ocsp.verisign.net? And what is the time to live for each DNS response? All right, so first we want to just make sure we understand what that time to live value is. Now, you're all familiar with the IP header and the time to live value here, but it's not the same. So we want to make sure that we're on frame 2. And then we're going to expand the DNS header. And I'm just going to drop this down here, pull this up. And what we want to do is take a look at the answers. We have both of those answers here. All right, so first we see the time to live is 381 for the first answer, and the second one, the time to live is 1. So when we take a look at that 381, that means that after 381 seconds, the entry will go away, and you'll have to issue a query again. All right, we'll pull that up. Now the next question is, in frame 2, what is the source port? All right, so we're going to drop this down, and here we can take a look at the user datagram protocol, and the source port is 53, which is associated with DNS. Now the next question is, a user agent in an HTTP header indicates the browser. So go to frame 7, right-click, and follow the stream. All right, we'll go to frame 7, right-click, and follow the stream. All right, so here we can see the user agent, which is Mozilla. Now, there are resources online so you can further define exactly what version that is on Mozilla. All right, we'll close that. Next, using the link in the document, you are to obtain a file and open it in Wireshark. Now, this capture is the DHCP DORA process, where we can see the 4-step process: discover, offer, request, and acknowledge. Now, we'll just pull this up so we can examine just all of these in general. And the question is, are DHCP messages sent via UDP or TCP? Well, DHCP messages are sent via UDP, which is a lightweight connectionless protocol, because you need the IP address quickly. The next one is expand the DHCP header in frame 1. So I'll go to frame 1 and I'll expand the DHCP header. The question is, what is the client IP address? And we'll scroll down here. And it says the client IP address is 0.0.0.0. And that's because the client doesn't have an IP address. The next question is, look at the parameter request list. And I'll scroll down here and expand the parameter request list. And the requests are what the client is asking, and those include the subnet mask, router, domain name server, and network time protocol servers. All right, we'll pull that up. And the last question is, what is the value of the transaction ID in all 4 packets? Well, it's right here, so we can see that the first 2 end in 1D and 1D, and the last 2 end with 1E and 1E. Now, the last step has us going back to CloudShark to examine a packet capture. Now, once here, we're to go to Analysis Tools and follow the stream. So we'll drop this down and follow the stream. And I'll scroll up here, and we can examine the entire contents of this stream. So the question is, did the FTP server require a password? Well, here we can see in plain text, anonymous login OK. Send your complete email address as your password. So no password needed, just a complete email address. All right, so that's your challenge. I hope you had fun. Built within Wireshark is the Expert System. The Expert System helps to alert the network administrator on possible issues once a capture's been made. Keep in mind it's only a guide. Sometimes it really isn't a problem, such as a checksum incorrectly calculated. When we go into the Expert Info console, you'll see 4 categories. I say Expert Info because that's how you might see it referenced if you go into the Wireshark Wiki. Now, they're in order of severity. The first one is errors. You'll see a red circle that indicates serious problems. Yellow indicates warning. That means there's possible problems. You'll probably want to look into them. Cyan are notes of interest. And the blue are chats, which is typical workflow and state change. I've opened up this packet capture because it's a pretty good example as it lists all 4 categories. Now, if we take a look in the lower left-hand corner, the red circle indicates the highest level of threat, that there's possible serious problems. So let's go in and select that. Now, when we go in and you can see the severity, and it is grouped by summary. Now, you can uncheck that and it would group it in a different way. But I like to keep it grouped together. If you remember, in Legacy, it had tabs. This way it's just on one page and you can see all of what's going on. Now the first thing that shows up is an error, bad checksum. And I'll blow this out. Now as it says, the Ethernet frame checksum is incorrect. Well, that might not be a problem. Let's exit out of here, and then we'll go back over to the Ethernet frame, anyone, and right-click. Go to Protocol Preferences, and here I say, validate the Ethernet checksum if possible. I'll uncheck that. And now you see it won't be an error. And again, that's a common thing. It's not always an error. It's just incorrectly calculated. Now let's go into the expert infos again. All right. Now when we take a look at any of those categories, you can blow it out and see those packets that it affected. Now here you see the cipher length must not exceed this certain length. And then there's malformed packets, and there's 160 of those. So those are ones you probably really want to look as to what is happening. Now then, the next category you see, there's some warnings. This one, DNS query retransmission, connection reset, and in this there's 25 connection resets. You'd want to know why were so many out there resetting. This frame is a suspected out of order segment. Then down below you see notes. Now again, this is things that aren't always critical, but again, you might want to look into those. There's keep alive segment, duplicate acknowledgement, and there's a lot of those, and that occurs, remember, the acknowledgement is expectational, meaning it's saying, I've got this much data and I'm ready for more, please send it. Now with the duplicate acknowledgement, it keeps duplicating and sending it until it times out, just simply waiting for the data. The last category is in blue, and those are chats. Remember, those are just some things that occur that aren't critical, certain things such as workflow, updates, or possibly state changes. Here you can see the state change connection finished, and we can see the passing of the FIN and the ACK flags throughout that. And there's quite a few of those. And here we see connection established using the SYN and ACK, and there's a number of those as well. So the expert system provides insight on possible issues in the packet capture. Wireshark groups are reporting by level of severity, and that includes errors, warnings, notes, and chats. Wireshark has many built-in tools to help the network administrator identify and troubleshoot network latency issues. Tools that include the expert system, coloring rules, the intelligent scroll bar, and the time values that are built into Wireshark to identify gaps in transmission. Within the expert information, there are several things that are cause for concern. That include zero window. That means that the client is unable to receive any more data because the buffer is full. Now on the client side, that might not be a big problem, but if it's a server, this could cause major bottlenecks. Keep alives that are saying keep this session alive, and duplicate acknowledgements, where the client is re-requesting the data over and over again until it receives it. Retransmissions or fast retransmissions, or what we call spurious retransmissions. A spurious retransmission is data that is sent again even though it's already been acknowledged. And that is because the server somehow didn't get that acknowledgement and it sends the data again. High latency can be caused by any number of things, such as processing delays, distance itself, and something called buffer bloat. This is a queuing delay, and that the router's buffers get full and the packets are simply dropped, and there's gaps in the delivery of the data. I've opened up this packet capture, and there are a lot of things going on with this packet capture. And I'll take a look if I go over to the expert information. And here you can see a number of things in the summary and the severity that I might want to take a closer look at. Over on the right-hand side, we can just quickly look down here and see a lot of black areas that we indicate that there are some problems. For example, let's take a look here where it says duplicate acknowledgement, number 17, number 18, number 19. What that is doing is saying that I've received this much data and I'm ready for more. Please send it. And it sends another one and another one. It's very patiently trying to get its data. What I'll do is follow the stream, and what I want to go to is there's two streams. We'll do 61, and let's take a look at that. In one of the graphs that is easy to identify gaps in transmission is the Stevens graph. Go to Statistics, then we'll go to TCP stream graphs and the Stevens graph. Now, this one is going back to the server, and that's just your acknowledgments. We'll switch directions. And here's where you can see these gaps in transmission. So we're getting the data, and then, as you see, we've stopped. And now we're getting a little bit more, and now we're stopped. Okay, so you're seeing some gaps and delays in transmission. And again, that's going to be adding to your latency issues. What I'll do is one more. We'll go to stream 45. And we'll switch directions. And this one's another one that shows you, well, we're getting the data, and then it stops. And then we get a little bit more. Then there's some stops, and then we're getting some. It should be a nice, slow, incremental graph, but it's really rare today to get that because there's so much congestion on the network. In addition to the Stevens graph, we can also use the time values to identify gaps in transmission. I'll have to find that conversation. We'll first go to Statistics and then Conversations, and then I'll have to filter down to that conversation. As you see here, 208 is the IP address. When I right-click, I apply as a filter, but I want it to go from the server to the client, and that would be B to A. And I'll close that. And now what you want to look at are the large gaps in between transmission. And when we first go in here, we're going to go to View, Time Display Format. And you want to make sure that it's set correctly. In this case, it says seconds since previously displayed packet, and that's what I want because now you can see that streaming in from the one source to the destination. And here you can see that first gap right here in between this packet and this one is 3 seconds, and we did see that one. And then we'll go down below, and this is the stream 45, and there's another one. That's a 1 second. And here's one that's 2 seconds. So in addition to the Stevens graph, we can use the time values to identify gaps in transmission. So Wireshark can help the network administrator identify and troubleshoot network latency issues, but the next step is to be proactive and identify where the bottleneck is occurring so that you can keep the data flowing. Sometimes when working with packet captures, you get a really large file, and you need to break it down to a smaller subset and send it off for analysis or keep it for later discovery. Now this packet capture down below, you see that there's 54,102 packets. Well, I just want to make it a little smaller, and we'll pretend in this case that the intrusion detection system set an alert that someone was going to a website and they downloaded something that somehow looked suspicious. So you pull off the file and you bring it into Wireshark, and since it was HTTP, let's just go through and do a filter. And we do a display filter by typing HTTP. Now the next thing is I don't want the online certificate status protocol, so I right-click and prepare as a filter and then say and not selected. Now remember, when I say prepare as a filter, it simply puts it up there for me to run to make sure it's what I want. Now I do want this, so we'll go up and we'll press enter. And then again, that will narrow it down just to those requests. Now one of the things we can do is export objects. Now within that, I'm suspecting that there was something that was brought in, and I want to go to see what that is. And I'll go to File, and export objects. And since we were at a website, we'll go to HTTP. And here you can see that there are a lot of objects. And these are all the objects that were within the capture. And this one, we'll take a look at this one. And we're not sure what it is. It says bluegoat.jpg. Now I'll say save. And I'll put it in this Wireshark folder. And then we'll close that. Now we have this smaller file. Now the next thing is we're going to save it. But first I want to put a comment on there so that I remember what it is I wanted to do. I go to statistics and then the capture file properties. And this just gives you a summary of this file. Well, down below I can put capture file comments and I'll put in there, not sure what's going on, but this traffic caused an alert. I'll say save the comments and then we'll close it. Now, if you do notice that the file name has a little asterisk, and once I save that, that will preserve the comments. But again, that was just something I did so that we could keep our reference for future when we go back into this file again. Now, the next thing is I'll go to File, and I could say Save As. Now, Save As is just as we've done before, where you can go in and save the file. And we'll just put HTTP traffic. And that is actually going to save the entire file. That's going to be with everything in it. And I'll say OK. And this case, I just want that subset. So what I'm going to do is go to File and Export Specified Packets. And we'll go to Export Specified Packets. And what we'll do is take a look at this. Well, first of all, I want you to see Save File as Type. And there's a lot of choices. What's really great about Wireshark is it's able to be imported into other applications. So you can see all these different extensions. And of course, we can bring them in from other applications as well. So we'll call this IDS Alert. Now down below, you can see the choices here is we can compress the file. And then down below, it says really what is it you want to save? And I could say all packets. And that would be captured, and I don't want that. This is why we did this. So we say displayed, or you can do selected packet, and that is actually the packet that we're on right at the time, which happens to be 25067. Sometimes I mark the packets, and that's not what I want, and I can actually do a range. So in this case, I'll say all packets and displayed, and we'll save that in that Wireshark folder. And now, we can close that, and then we'll go back in, and we'll look at the recent one we had just gotten into, and we'll clear the filter off, and then you can see the entire stream. As you see, we've got all the HTTP traffic. So the last thing we'll do is we'll take a look actually as to what is it I did export. And remember, you can export those objects, and we'll just open up Blue Goat. Oh, well, doesn't seem like there's anything bad there, but it's always good to investigate. So with Wireshark, we can take a huge file and we can subset that. We can add a comment and then export only those selected packets. CloudShark is an online packet analysis tool that provides an interface similar to Wireshark. In this segment, we'll evaluate CloudShark's built-in analysis tools and discover ways the file can be evaluated online or downloaded and analyzed with Wireshark. I'm here at QA Cafe, and I'll select Analysis Tools, Personal Software as a Service. Now, once here, you can log into your account, or if you'd like to try CloudShark, scroll down, and you can sign up for a 30-day trial by completing this form. I have a basic account. Once in, as you can see, I've uploaded several packet captures. I'm going to open Interesting Object, which brings us to the CloudShark interface. Now, once here, we can check out some of the analysis tools. And I'll go over here and drop this down. Now, once we drop down the menu choice, we see a lot of options. For example, let's try follow the stream. Now, this is similar to Wireshark, where we can see the entire conversation. And I'll close that. In addition, there are a few graphs. Now, one of the more powerful analysis tools is threat assessment. Let's talk about how you can use this feature. For example, you're at the office and clients are complaining about slow response times. So you grab a capture and then upload the file, which I have here. Now, once you upload it, you can make it public and then you can share it with your team. And then you can all examine the file together. We'll open the file. Now, once I'm here, I'm going to check out a couple of things. Because there was a lot of traffic on the network, I'm going to look at GeoIP world map, and I'll select that right there. Now, this tells us where the endpoints are located. And you can see that there seems to be a lot of different countries where there's endpoints. Now, if I want to see the total bytes exchanged, we'll scroll down here to see the statistics. And here we can see a number of different countries and a lot of packets that have been exchanged. Now I'll close that. Now, another analysis tool I like to use is threat assessment. We'll drop this down and go to threat assessment. Now, this shows several levels of severity. Now, once here, we can click View Advanced Threat Analysis, and I'll open it in a new tab. And once in, you can examine the results. In this case, we see possible dry decks, which will prompt me to do additional research to learn more about DryDex malware and how we can mitigate this threat. So now let's go back to interesting objects. Of course, we can do our analysis here, but we can also export the file and open it in Wireshark. And I generally download the original file, download it, and open it in Wireshark. Now, once in the file, I want to see what interesting object there is within this file. I'll go to File, Export Objects, and HTTP. There we see an image. So I'll say Preview. And there's the interesting object. So CloudShark has several built-in analysis tools, so you can evaluate the file online or download and analyze with Wireshark.